Intervals of concavity and points of inflection. No critical numbers. So no derivative equals 0, right? Equals 0. So make sure you understand that you're going right to the second derivative. So first derivative would be 4 over 3x cubed, x cubed, minus 12x. Go right to the second derivative. So that gives me 4x squared minus 12. Okay, I want to find out where this for a second. Intervals of concavity. So when the second derivative is positive, f is cupped up. And when the second derivative is negative, that's when f is cupped down. So you can do a sign chart. I'm thinking that this is a pretty easy graph, right? It's just a parabola, shift it down by 12, right? Negative 12 down there. I think I can set this equal to 0 and find out what those numbers are, right? So if I set 4x squared minus 12 equals 0, I see I get x squared is 3, x is equal to plus or minus root 3. So that's what these two values are, root 3. All right, so when, I should label my graph, this is my y double prime. So where this graph is above the x-axis, that's where the function is concave up, right? So, f of x is concave up from negative infinity to negative root 3, and then from root 3 to infinity, because that's where the y values on the second derivative are above the x-axis. Okay, so let's look at where the second derivative is less than 0. So that's between these two, right? So if the second derivative is less than 0, that means f is concave down, and that would be from negative root 3 to root 3. So are there points of inflection? Yes. So the points of inflection would be this and this, because it changes from positive to negative and negative to positive. So the points of inflection, and I'm always just going to ask you the positive, the x values. So it's plus or minus root 3. Okay, so let's go to this is different. So I want to make sure you're contrasting second derivative test with the second derivative, what tells you the concavity. So second derivative test is asking you to find the maxes and mins, right? So that's where you do need the critical numbers, right? Find the critical numbers. And so if it's second derivative test, they have to be this kind of critical number, right? So f prime is 4 thirds x cubed minus 12x. Set that equal to 0. And let's see what that gives us. Let's see if I set, well, I've got the 0 over there already. Okay. Is there anything I can factor out? Yes. I think I can factor out a 4x. That'll give me a 1/3 x squared minus 3. So that gives me x equals 0 and 1/3 x squared minus 3 equals 0. X squared is 9. So x is plus or minus 3. So what do I do with that? I plug those critical numbers, this and these two, into the second derivative. Okay, so find the second derivative. So I get 4x squared minus 12. Oops, that's double prime, right? Okay, so now let's go do it. So I'm going to plug f double prime. I'm going to put x equals 0 in. If I put in x equals 0, I get negative 12. That's less than 0, which means concave down. So that means f of 0 is a local max. All right, let's try another one. Let's try to plug in negative 3 into the second derivative. So I have 4 times 9 minus 12. Well, that's definitely a positive number. So that means f of negative 3 is a local minimum, because it's cupped up, right? And the same thing if I do f of 3. I get 4 times 9 minus 12, which is bigger than 0. So then I get f of 3 is a local minimum. Oops, sorry, I forgot to write down. F of negative 3 is a local minimum. Come back. So f of 3 is a local, f of negative 3 is a local minimum, so is f of 3, and f of 0 is a max. Alright, so let's come down and do this one. Just like before, I was saying it's wise to start with your critical numbers. So derivative equals 0. Let's check it out. I see it's equal to 0 at negative 2 and 2. Right? Okay, so now let's go check out where the derivative doesn't exist. Where does the derivative not exist? So the derivative doesn't exist at x equals 0 and at 3. And I neglected to say here, but I'm always going to say that the original function always has all reals in their domain. Okay, let's look before and after negative 2. Before negative 2 positive, after negative 2 positive, no max or mins, right? Let's look at 2. Before negative 2 positive, after negative 2 negative. So I'm not even going to write it down because I think you're so good at this now. F of 2 is a local maximum, right? What's happening at 0? Before 0 it's positive, after 0 it's positive, no max or min. What's happening at 3? Before 3 it's negative, after 3 it's positive, so f of 3 must be a local minimum. Okay, so let's start to just draw a little bit of a picture, and I'm going to take liberties and kind of use some space up here. Remember, max and mins give you a start, and then we can do the increasing, decreasing. Right? Because you can't, no one can just draw the graph right away. So you always have to start little bits. Okay, so let's see. Minimum at 3. So minimum at 3. So I'm just going to make it there. And then maximum at 2. 2. Okay. Oh, but wait a second. This minimum at 3, it's not a bottom of a parabola. It's some kind of doesn't exist thing, right? So that must mean it's like a pointy thing. Probably a cusp. We'll be able to enhance that and figure that out. So I got the maximum and the minimum. The maximum is the slope 0, so nice top of a parabola. Okay, so let's look and see what we got going on here. So anytime the derivative is above the x-axis, that's where the function is increasing, right? So here's negative 2. So I have increasing slope 0, right? Because that's what that means. And then increasing again. And it's still increasing, right? So increasing, oh, wait, sorry about that. Derivative doesn't exist, so something bad is happening. And it's still increasing. So what bad could be happening there? That's got to be a rotary tangent, right? So I'm just going to move this little cuppy thing up further, right? Because we always have to do these in pencil, because you know they're going to be joining pieces together. So between 2 and 3, it's decreasing. And then after 3, it's increasing, right? So we got the ups and downs, I call them. Now let's go check on the concavity. So where f prime is decreasing, that's where f double prime is less than 0, and that's where f is concave down. So decreasing, decreasing, and decreasing, right? So it's decreasing from negative infinity to negative 2. And then from 0 to 3. And then again from 3 to infinity. So let's make all of those cups down. So cupped down, and then cupped down. Oh, that makes sense, right? All the way to here. And then cupped down again. There we go. And so where is f prime increasing?